In the previous episode, we talked about different phenomena shown by light and the wave model to explain those phenomena and the particle model to explain those phenomena. Newton, who did lots of experiments on optics in his house, he was firm believer of this corpuscle model. Light is nothing but collection of high-speed particles. Alright, the particles do not have mass, they do not have, they are not material particles, but that light is separate entities, and those corpuscles are coming from the light source. So that was his firm belief, and based on that he explained everything, all observations of rectilinear propagation and reflection, refraction, diffraction, interference. Newton was well aware of diffraction and interference. Right? Newton's rings, very famous experiments in our BSc syllabus everywhere. Newton's rings, that is based on interference only. Okay? But then there were another school of thought that no, light should be some kind of a wave in a medium. In the hypothetical medium, ether was common. Everyone believed that yes, in space you have ether in which things move. So light is a wave phenomena in ether. That was another school of thought, and they also explained rectilinear propagation, reflection, refraction, everything, diffraction, interference, everything. So that was, let's say, 18th century. That is almost whole 18th century. These things were there, but then basically, this corpuscle theory dominated over wave. Speed of light was something which could decide, but that time speed of light in water or in medium was not available, and therefore that did not have a role. Okay. Now we come to 19th century, 1801 onwards. 1801, Thomas Young did a double slit experiment for the first time, and after that there were a number of studies on diffraction and interference, Fresnel, Fraunhofer, Airy. So those experiments brought this wave theory on top. Okay, and 19th century it was wave theory. Light is wave. Whoever wrote in examinations light is wave got full marks, and so on and so forth. So that is how it went. And then speed of light in the laboratory was measured after this. Michelson developed very good setup where you can measure the speed of light in a hall. Okay, of course nowadays we can measure it on a tabletop, but those times, and that also gave a verdict in favor of waves. Alright, so the entire 19th century, light, there's no doubt, very clearly it has to be a wave phenomena. Independent of all those things, there were people who were trying to study the radiation in the wavelength distribution of radiation, right? So light is also radiation, but when I say radiation, the wavelengths, or it can be invisible. So not only infrared and ultraviolet, any kind of wavelengths. So let us think of sunlight. As we know, sunlight contains several wavelengths. Now we are talking in terms of the waves. Radiation is waves. So it has visible wavelengths from 400 nanometer to 700 or 750 nanometers, that range. Then infrared, more wavelengths, larger wavelengths. Then ultraviolet, smaller wavelengths. Much smaller wavelengths, much larger wavelengths, and so on and so forth. So all those wavelengths are there in sunlight, but not in equal proportion. So we can draw a curve. One side is say wavelength lambda, and other side something called u lambda. I'll just tell what it is. It is essentially a measure of which wavelengths will have more energy and which wavelengths will have less energy, and how that energy varies with wavelength. So dominant contribution is coming from which wavelength range and so on. So I'll just define that, and then it is something like this. Let's say it's something like this, and there's a maximum at certain wavelength, and for sunlight this is around 500 nanometer, around 500 nanometer green range. Okay, so you have if you take some 5 nanometer interval here around this 500 nanometer, you will have certain energy. If you take the same 5 nanometer interval here, the energy will be less. If you take the same 5 nanometer interval here, the energy will be even less. If you take 5 nanometer interval here, the energy will be less. So it goes through a maximum. And this is in fact, if you take certain range, say this is delta d lambda. So the energy contained from lambda to lambda plus d lambda per unit volume, that will be u lambda into d lambda. So that's the meaning of this u lambda, but you don't have to go in that great detail. After all, it is a story only. Alright. So basically, which wavelengths are having more contribution in that sunlight, which wavelengths are having less contribution. If you plot that, it goes to a maximum, and for sunlight it is at somewhere around 500 nanometers. Now, if you don't see sunlight, something else, and especially suppose you have a room, suppose you have a room closed from all sides, or just a box maintained at certain temperature T, and the radiation which is here inside this, and if you ask similar curve for this radiation which is maintained at temperature T, so that will depend on this temperature T. Okay, if your temperature is say room temperature, right, room temperature, then it will be something like this. This curve will be something like this. Very large wavelengths, this maximum will occur. Total energy per unit volume will also be less, and this maximum will occur at a very large wavelength. But if you maintain it at certain temperature, let us say 1000 Kelvin, then this will be shifted. Then this will be something like this. So this maximum is shifted. And this sunlight corresponds to a temperature of something like 5000 or 5500 Kelvin, which is the temperature of the surface of the sun. If you go still beyond that, this will shift here. So experimentally, this relation between the wavelength at which you get the maximum contribution in the radiation and the temperature, that relationship was studied, and it's known as Wien's displacement law. Very simple relation, very simple relation. Lambda m, where it maximizes, into temperature is constant, and that constant is 2.898 into 10 power minus 3 meter Kelvin. Meter Kelvin. Wavelength is length and temperature is in Kelvin, so meter Kelvin is the SI unit. So the simple thing. Inversely proportional to temperature, this lambda. So this was one observation, people know about it. Then another one, you have you take some kind of, let us say, a surface, some surface area A, right? Some material body, hot material body, and then it emits radiation. It emits radiation. So how much energy is emitted? Total energy, all wavelengths taken together. Total energy, how much total energy is emitted per unit time, per unit area, right? And that is once again known as Stephen's law. Also experimentally known that U is equal to some constant sigma times t to the power 4.
Sigma equal to some 5.7 into
10 power minus 8, and the unit will be energy per unit area. So energy will be joule per second, that will be watt, right, per unit area. So meter square here, and temperature, so Kelvin to the power 4 here. SI unit, you just work out the SI unit. SI unit of this and SI unit of this, and you can work out. So this is also a constant, universal constant. But then what kind of surface it is, that will decide. You have to put some factor k also here. Maximum is k equal to 1, and otherwise k will be less, but with the same surface. If you change the temperature, same k, and u will go as t to the power 4. That is Stephen's law. These two were experimentally known, and people had developed theory using that wave model, the classical theory, and they could get, okay, fine, it should be like this. Very good. That's okay. But then the other effort was to find the shape of this guy. If I know the temperature, to find the shape of this, to develop a theory which can give me this result, that variation of this u lambda
with t
should be of this type. That was a challenging job. That was a very challenging job. The wave model which was there for radiation, very well established, explained so many phenomena, but then to produce this kind of dependence, that theory did not work. Since temperature is there, a lot of thermodynamics will be there. Okay, so radiation in equilibrium with material. So you have material here, these walls, they are absorbing radiation, and they are also emitting. So all these things have to be taken care of. So the theory has to be developed taking this into account. And all the known theory of that time, when they were applied, people did not get this kind of thing. What people got was something of this sort. Though this energy, this u lambda will keep on increasing and will go to infinity as you go to very small wavelengths. Absolutely absurd. Again, totally not matching with what it is. So that was a big challenge in 19th century. And then comes Max Planck, and he also tried various ways. It did not work out. Then he had to do something drastic. He had to make an additional assumption in the theory. Okay, and that assumption was turned out to be the foundation of all that quantum mechanics which we have, based on which we have semiconductors, based on which we have everything. So the whole electronic world is based on that. So let's talk about that Planck's assumption or Planck's addition to the theory, or the new component in the theory which was injected by Planck. Let's talk about that. So suppose you have an enclosure and maintained at a temperature T, and then it has radiation, and the radiation is falling on the wall of that enclosure, and part of it will get absorbed per unit time, and then it also emits, that material will also emit. So there will be an equilibrium and the temperature will be maintained. So if you have maintained the temperature of this enclosure, and then you have radiation inside. And the purpose is to find the distribution of energy in different wavelengths once the temperature is given. So that's the goal. That curve has to be reproduced. Now, what Planck does is something like this. Suppose you have the radiation falling on this wall and getting absorbed. And think of the component of this radiation which has a frequency nu. Right? This will have varieties of frequencies, varieties of wavelengths, but wavelengths and frequencies are all related to each other because you know the relation. Lambda is equal to C into capital T, which is 1 by nu. So you can talk in terms of frequency nu, or you can talk in terms of wavelength lambda. This C is fixed, 3 into 10 power 8 meter per second speed of light. Okay, so this radiation which is coming and getting absorbed here in the material, think of that. That will also have varieties of wavelengths and varieties of frequencies. So consider that component which is having frequency nu to nu plus d nu, we can say. So consider that component with frequency nu. Now what will this do? What will this do? Remember, this is we are talking of 1900, and already Maxwell's equations were there. Another huge support to wave theory. Not only that light is wave, light is electromagnetic wave, and this support comes from a very unexpected quarter. Maxwell is working on electric field, magnetic field, not on radiation, not on light. But then he comes out with the equations which tell, okay, there should be electromagnetic waves with speed 3 into 10 power 8 meter per second, and already light is there. This radiation is there traveling with that speed. So those things will be there. So if this radiation of frequency nu falls on the material and gets absorbed there, what will it do to the material? The unit which is absorbing, that will start oscillating, because you have electric field and magnetic field all oscillating with certain frequency nu, and that will exert force on the material, the electrons there, and therefore the thing, whatever is available there, will start oscillating with that frequency. It's a solid. So atoms are all bonded together, some kind of a lattice is there, some kind of crystal is there. So there also you have varieties of units which can oscillate, right? It's not gas, it's not atom. So we will not say that this radiation is absorbed by this particular atom and the electron of that atom started oscillating. It's a kind of a whole structure, but still you can think of in that material that you have units which can vibrate, can oscillate, and if this radiation is absorbed there, it will get those units into oscillations, right? So they are known as oscillators. They are known as oscillators, and each oscillator will have its own frequency with which it can vibrate, and so that component will be absorbed dominantly, and if it emits, it will emit with that frequency only. Okay, so those kind of units, you assume those kind of units on the material which can absorb and which can emit and with certain frequency. Each oscillator will absorb and emit a certain frequency. Okay. Now comes the Planck's hypothesis or assumption or addition to the existing theory, whatever you name it. If an oscillator of the material absorbs radiation of frequency nu, it can do so in one go with energy Nh of radiation. Let me see if it makes sense. If an oscillator of the material absorbs radiation of frequency nu, so suppose it is falling here and a particular oscillator is taking that energy, so it has to absorb that particular component of this radiation. So if an oscillator of the material absorbs radiation of frequency nu, it can do so in one go, right? In one go, how much energy it can absorb? It can do so in one go with energy Nh nu of radiation getting absorbed. So in one go, in one single blow, only this much of energy can get absorbed in this oscillator. So this is it. And what is this? What is this N? This N is a positive integer. This H is a constant, and nu is of course frequency. Right? From where it comes? Mind of the Planck. Okay, that's all. Not that okay, you don't have to justify or it's because of this, because of that. No, nothing works at this. And it works. Similarly for emission, if an oscillator has to emit, if it is absorbing, it also has to emit, otherwise the temperature will not be maintained. So if a particular oscillator is emitting, just in this sentence perhaps we can do that. If an oscillator of the material emits radiation of frequency nu, it can do so in one go with energy h nu, n times h nu of radiation getting emitted. Just change these two sentences to words and it tells that how it emits. So each oscillator, when it absorbs radiation of frequency nu, it can absorb energy h times nu, or double of that, or triple of that, or 10 times of that, or 17 times of that, or 217 times that. Positive integers times h nu. Only in those units it can absorb. And the probability, which one is more probable, which one is less probable, for that you have usual laws, higher energy than the probability is like e to the power something. So those existing laws are applicable. Okay, and similarly for emission, if it emits radiation of frequency nu, in one go an amount n times h times nu will be emitted. So it is quantized. First time it is quantized. Energy is quantized. You cannot absorb arbitrary amount of energy. The oscillator cannot absorb arbitrary amount of energy. 2.37 times h nu. No, that cannot be absorbed, right? And over a period also, if you add how much the total energy absorbed, that will also be integral multiple of h times nu. And similarly for emission, it cannot emit arbitrary energy. It has to emit in units of this h nu, steps of this h nu. So this is that additional assumption which he includes in the existing theory and then works out the usual methods. And then he finds the equation, whatever equation for this u lambda versus lambda, and he reproduces that curve extremely well. Extremely well. Okay, so by properly choosing the value of h, the experimental data and this theoretically calculated curve from the equation that he gets matches extremely well. Okay, so that's the only justification why it is there. So this is how this Planck's brings in quantization into physics, and once it was there and many more things came up supporting that, yes, it should be like this quantum should be there and all those things. The entire semiconductor physics is developed because of this quantum character, and because of that semiconductor revolution, we have so much of electronics working and so on. So this is the starting point of that quantum hypothesis. So we will pick from here in the next episode.